Right, good morning. My name's David Conway. I'm Materials Technology Director for Tods Aerospace and Tods Defence. I'm going to talk to you this morning about transformation of production techniques that we've used from hand lamination. And when I say hand lamination, I mean not prepreg, I mean literally resin and glass or carbon hand lamination. Tods as a business was established on the south coast in 1935 as a traditional boat builder. Tods was one of the first companies to actually use composites to manufacture boats. We now specialise in the design, manufacture, installation of composite components, assemblies and structures. A lot of what we do is exported, and we've got the normal accreditations you'd expect from a company, an SME of our size. We have a number of business areas. This is some of the products from our aerospace. These are floor plinths that are thermoplastic, which are used for mounting business and first class seats. So you can see an interior of a cabin there with the plinths, with the furniture, etc. that's been fitted. We do a lot of aircraft structures. These parts are from AW159, which is the Westland's latest offering, which is Wildcat. We manufacture 140 parts, 40 of which we've designed. We've also got defence business. One of our specialities is acoustic enclosures, sonar domes. You can see a sonar dome just there underneath the sea, so you can see they're very, very prone position. We do a lot of work for submarines and also Radomes. Our existing products historically have been sonar domes and geodesic radomes, which historically have been hand laminated. Really what we're looking for, well, I suppose one of the overall criterion, is we don't want to increase costs. If we can reduce costs, we're interested in that, but mainly it's about improving the performance of the products that we make. So by going to closed mould techniques, you get better thickness control, lower void contents, higher fibre contents to maximise your strength. We've found that these techniques reduce costs and rework, and because of the increased consistency of the quality, you can reduce safety factors, which prevents over-design, keeps your cost to a minimum. And also, if you're using particularly polyesters, vinyl ester resins with open moulds, you've got health, safety and environmental issues. So we were at the time that we wished to see what was on the market, do some test panels, test pieces ourselves, and we did some development on all of these techniques. That is low temperature out of prepreg, resin film infusion, and rift or resin infusion. We were confident that all of these techniques would actually achieve the quality that we require. It's really a matter of what ones were most suitable for our applications. So just a bit of information about the different methods and the advantages or disadvantages as we see. So with low temperature prepreg, it is what it says. It is a pre-impregnated material that's applied to a mould. You usually vacuum debulk the first layer and then subsequently every 4 layers. You then apply the normal peel ply release film, etc. Apply a vacuum and cure it typically at 85 degrees. When you consider particularly sonar domes, one of the major issues that we have is actually holding the materials in place prior to applying a vacuum bag. So low temperature prepreg scores very well. It's got tack, it will stay literally where you put it. The resins are relatively easily toughened. Most low viscosity vacuum infusible resins aren't toughened because the toughening agents actually increase the viscosity to make it, and it makes it difficult for you to actually infuse with. The quality, our experience was the quality of laminates were very good. But the disadvantage is the debulking. If you're doing something like a sonar dome that's 8-9 meters long, 3 meters wide, 2 meters high, it's a major undertaking to do that debulking. The material costs are relatively high, and you need an oven. The second method that we considered was the resin film infusion method, where you've got alternate layers of epoxy resin between fabric. You apply the material to the mould until the thickness is achieved. Again, you bag it using the traditional materials of release film, breathe the fabric, vacuum bag. You assemble and then apply a vacuum. You then heat the mould, and obviously its contents, to approximately 75. At that temperature, the viscosity of the material drops, and under the influence of the vacuum, infuses your product. You then increase the temperature to cure the resin. Despite Airbus's results, we've found that we can get very good quality, less than 2% air content, but we are talking about a far lower temperature material, which I think is probably more optimized for this product than the materials that Airbus were using. One of the major advantages is you don't have to debulk. You put in as much as you want, then you vacuum bag it and cure it. So you're not tying up a lot of time vacuum debulking. The resins, again, are easily toughened. We find very good results with certainly the void content and reproducible resin content. Material costs, again, are relatively high, but the major disadvantage is you have tack, but it's not a lot of tack. So you can hold it in place, but you do need additional aids to be able to do that. And also you need an oven. Rift resin infusion under flexible tooling, there's a number of names for it. Basically, you lay up into your mould, dry material, you bag it with a vacuum bag and the normal accessories. You apply a vacuum, and then you introduce low viscosity resin into the bag, and it goes through it and infuses. The properties of the component can then be improved by post-curing. And if you're careful, you can actually post-cure out of the mould, which has its advantages. Again, you don't need to do multiple debulks. The materials are very low. They're just fabric and resin. There's a limit to what toughness you can achieve, particularly with epoxy systems. As I said earlier, the toughening agents that put into epoxies tend to increase the viscosity to a point where you can't readily infuse. The downside is there is no tack. If you've got there are materials that you can use to spray on, but we've found that they're not that effective, particularly when you've got difficult shapes and very thick laminates. So the first case study, a Sonar dome. This is Type 45, which is a destroyer that BAE are making for the UK Navy. You can see that work, that's the front of the ship, and that's the dome that fits onto it. It's there as a sonar window. It protects the array from damage, it minimises flow noise, and it creates a quiet environment so the sonar can listen for other ships and other targets, rather than just pick up noise from the ship itself. It's made of a number of components, as indicated. Now, the aft section, which I'm not talking about today, the shape is too narrow to manufacture in a female mould. Literally, you can't get in there to laminate it. Therefore, we actually make that with syntactic foam and overwrap it with composite. The longitudinal support and acoustic baffle, that is actually vacuum infused again, I'm not talking about that. The sonar array. What I'm going to be talking about is the actual dome shell, which is glass. This dome is the blue area. The blue area is the acoustic window, which is, press the right button. The blue area is the acoustic window. That's 25 millimeters thick. The red area on the base is 100 millimeters thick, and the flange area is 75 millimeters thick. So it's quite a big structure. Now we chose, again, this is a completed dome, and you can see the difficult shapes that you've got to deal with. So when I was talking earlier about how much tack and how easy it is to hold things into position, that's a major issue for us. We decided that we would manufacture it in a female mould using glass RFI. Principally, we could have achieved the quality that we required using low temperature prepreg, but because of the debulking operations, where you'd be debulking this every day, economically it just wasn't viable. The time to achieve and the cost of achieving it would have been too much. So that's the mould that we use. We use traditional mould manufacturing techniques. That's a pattern, and it's a high heat distortion temperature polyester resin. Whilst we were looking at changing what we were doing, there were simple things that we did, such as, you can see there's a walkway that's actually part of the dome mould. We used to use scaffold, so you've got the time and the cost of scaffolding. By simply incorporating your walkway as part of your mould, it makes it far easier to move around, and you haven't got the additional cost of scaffolding and time. This is the oven. Well, in actual fact, it's more of a heated workshop. We can take it to 100 degrees centigrade. The structure itself, well, I was looking for a building that was a reasonable cost, that was well insulated. So I went to the supplier of industrial freezers and fridges. So it's standard technology for industrial fridges and freezers. So cost-wise, it's not unreasonable. It's 200 millimeters of rock wool. So when the oven actually is at 100 degrees, you can't feel the temperature on the outside. It's that well insulated. We've got 4 18 kilowatt heaters that we use for heating it and controlling it. That's the completed dome shell. It's 7 meters long, 2.4 meters high, and about 3 meters wide. So it's about 2.8 tons of composite. That's the completed dome itself as it goes to the customer, which has got some damping treatment on the outside. The tack is very dependent on temperature. So we effectively air condition the room. If the temperature is too hot, you've got too much tack. You can't easily move the material. If it's too cold, you've got no tack at all. You need some sort of clamping system to hold the material on the top of the mould. If you don't do that and it slumps, it's impossible to get it back into its original position. Because of the relatively low temperature cure, these materials are quite lively exotherm-wise, so we minimise the maximum thickness of cure at any one time to 20 millimetres. And also you need to check the temperature vacuum of the mould, air and the laminate constantly. And also particularly with the vacuum in several places. Because it's such a large structure, you can be measuring the vacuum on one side of the dome, and at the other end you've actually lost vacuum through a leak. So we constantly monitor, we have people there monitoring during the cure process, and if necessary, particularly at a lower temperature, if you get a leak, they go in and fix it. Overall, it's cost neutral. The materials are more expensive than, say, the vacuum infusion. But compared with a hand-laminated dome, there's a significant reduction in labour. But really the most important thing is the increased strength and reproducibility and quality. If you've got a hand-laminated dome, then typically the resin drains from the top of the dome down to the bottom, so the thickness varies. You've got two teams of people, one working either side. They tend to work slightly differently, so you can get thickness differences. And also the air content is relatively high. And the other thing we achieve is reduced production time. We design, manufacture and install radomes, down to small radomes for submarines, up to large geodesic radomes. This is a radome, or two radomes we did for Svalbard, which is an island, I think about 600 miles of the Arctic Circle. They're tuned to transmit at specific frequencies. You tune them by the properties of which is a foam core, so it's the properties of the foam core, the thickness of the foam core, and the thicknesses of the skins. And they're there to protect the antenna, and also it sheds rain, snow, etc. effectively. If you get a build-up of rain or snow on an antenna, then obviously it doesn't work. Now this particular one is glass fabric, aramid in the flange to improve the bolting area, 1mm glass skins, PVC foam, polyester resin, and the process we decided was RIFT, or Resin Infusion. The main reasons being that it's a simple shape. You don't have any problems holding the material where you want it to hold. The properties which you get are very good, reproducible, and it's a low-cost method. The materials. That's a typical panel in manufacture. I think it's fair to say, particularly about mould tools for any of these processes, you really need to start from scratch. We used to use, for the radomes, we used to use moulds with bushes so we could actually drill in mould drilling. Well, as soon as you've got holes in your mould, you're struggling with vacuum. So we took the principle that we would do monolithic moulds and have separate drill jigs, which works very well. There was a total of 228 panels, which the radomes were installed within the Arctic Circle. We also found that because of the process, the quality of the process, the dome actually fitted together better. With hand lamination, you do get slight variations in curvature, etc. This actually is the best dome that we've ever done. We made a point of actually checking what our productivity was like compared with previous hand laminated panels, and we saw a 40% reduction in labour. I think it's fair to say the more complex your layup is, or the more stages there are, then the greater the savings. So if you're manufacturing one of these panels, obviously you need to gel coat. You would then lay down glass by hand lamination, let it cure. You'd then apply adhesive and vacuum down your foam, let it cure, and then you'd laminate over the top and let it cure. So you've got something like 5 stages, whereas with this stage, you gel coat, you put your materials on, you bag and you infuse. So, as I say, basically the more complex the layout, I think the more potential there is for savings. Production time, again, because you're not going through all those stages, it's a far quicker process. It's not uncommon with sandwich panels that have been hand laminated to get dry patches and blisters. I think it's fair to say that just did not occur on any of these panels. One comment that I've had from other people rather than own experience is because the resin content is far lower, your laminate actually comes out a lot thinner. It's just a matter of taking that into account. And it's a similar materials cost to hand lamination. So your real saving is in your labour. How much time have I got? 5 minutes?
Yeah, another 5 minutes.
Just to show that we didn't do this as a one-off, I'm just going to go through some of the products that we've made over the years. I won't go into detail, just to show you, we do not hand laminate these sorts of things anymore because of all the advantages we've found. This is another sonar dome, which I've got a few of. This is one that we did for the Norwegian Navy. It's a glass carbon sandwich structure. The only reason we put glass in the middle was to reduce the cost, because the glass on the inside, sorry, the carbon on the inside and the outside is doing the work. This needed to be carbon because it's got a sonar that looks downwards, and the main load case for this is slamming loads, where the ship actually comes out of the sea and then slams back down again. Normally you would just put, as the previous one, you'd put some sort of structure between the ship and the base of the dome to strengthen it. We couldn't do that, therefore we needed to use carbon. This is one that we've done for Raytheon in the States. We've actually got some quality awards from Raytheon for the work that we've done with them. This is for a development destroyer. We've made 2 domes, and we did think at one stage that we'd done the design, that maybe the Americans would want to make them themselves, but we've actually done the manufacture. Again, this is RFI. This is a Keel Dome that we've done for the Indian Navy. I think we've made 4 or 5. Again, this is carbon due to the, quite honestly, it's a bad shape for strength, but it was their design, their hydrodynamics design. One of the things with the carbon structure, particularly for a sonar dome, is it rings like a bell. And so self-noise is an issue. As it goes through the water, it creates noise. The sonar picks up that noise. We actually developed a constrained layer dampening process material, which it's a polyurethane material that we put in partway through the laminate, that we have tuned for the specific frequency and temperature that it operates at. This is a submarine bow array window, which is for the Spanish Navy, which is a new submarine that they're building at the moment. You can see it's quite a big structure. It's too big to transport to Spain, so it's actually made in 3 parts. There's 1 part there, 1 part there, and 1 part there, and it's in a frame. So we send the frame over in parts, which they assemble. They then assemble the 3 parts of the acoustic window onto it, and then offer it up and fit it onto the submarine. This is bridge fin window, again submarine window, which is on the Astute class submarine for the British Navy. Submarine casing panels. This was a development program that we did for the MOD in conjunction with Kinetic. A lot of submarine casings, but the casings is the area that you walk on a submarine. I can't show it for security reasons, but underneath the stiffeners there's actually dampening treatment that's part of the layup. So again, it's a sort of self-noise issue. This is a project that we did with BAE as a lead, with a couple of other companies, where we were looking at getting Bragg gratings, fibre optics, into composites for naval applications. And this is vacuum infusion. So the development was of the connectors, the fibres, and actually how you fit them into a vacuum infused process or product. I did allude earlier to other radomes that we do. This is RFI. We are specialising in designing radomes for submarines. They're air-backed because they only operate obviously on the surface. So they're effectively pressure vessels. So you've got the competing requirement for radio frequency transparency, but also withstand the deep diving depth. This was unusual for us. It was a build-to-print job. Again, this is vacuum infused. It was from Bombardier. When I say people movers, they're these little train things that are at airports that shuttle people backwards and forwards. We did 70 of these panels, and there were 4 different panels, so it was 70 by 4. One of the lessons we learned there was print through is a major, or can be a major issue with vacuum infusion. This contained balsa wood block, and as I say, it was build to print. They supplied the moulds, they gave us the layup, and then they weren't happy with the cosmetic appearance that we got, because you can see the blocks through it. It was qualified for fire performance, so they were unwilling for it to be rubbed down and filled and painted. We did develop techniques that they compromised a bit, plus we improved the quality of what we were doing. And the main thing is that, you know, print through is caused by shrinkage of the resin as it cures. If you can get your resin, to cure on the mould face first, you can limit the problems that you have. Right, just to confirm that it's, you know, I would say at times there have been problems which we've overcome and worked together, and it's been a very positive experience. I think it's fair to say, particularly with the Sonar domes, if we hadn't moved to improve the quality, cost, etc., we possibly wouldn't be in that business now. You do get to a point where, you know, customers' expectations change, the technical requirement changes, and if you don't respond to that, then it's not good for the business. So, higher strength, good thickness control, low void content, cleaner manufacturing technique, I'd recommend it.